So we are talking about Taylor series, and this right here, which I've written, is the formula for the Taylor series. I'm not sure if I ever wrote it exactly like that last time. Probably, I think last time I just wrote something like the formula for the constants. The constants, the formula is 1 over n factorial, the nth derivative evaluated at 0. All right? This actually is the Maclaurin series, which is usually what we're going to do. The Maclaurin series is the special format of the Taylor series, which is centered at the number 0, which is what I wrote up there. You can do the Taylor series centered at another number, although for this class we're mostly going to stick with the Maclaurin series. All right, we did some examples last time. The important examples that you should know are this one, 1 over 1 minus x, which is just sums of powers of x. No funny business. And then we also did e to the x, which is sums of powers of x, but with the factorials in front of them. 1 over 3 factorial x cubed, etc. All right. Today I'm going to do sine and cosine, which are the sort of will round out our list of our favorite functions. So let's try sine of x. I'm going to do sine of x all together, and then I would like you guys to try cosine of x on your own. It's very similar to sine of x, as you might imagine. So what do we got to do? We got to find these constants, right? These things, which involve derivatives of the function, taking the derivative over and over again. This is not so hard to do with sine. It's very easy to do with e to the x because you get the same thing every time. With sine and cosine, it's not so hard to do. So I'm going to start by writing f of x is sine of x, of course. And our first constant is not using the derivative at all. It's just f of 0, if you look at that formula for the Taylor series. So this would be sine of 0, which is 0. So the first constant in the power series for sine x is going to be a 0. Okay, let's continue. The next one is the derivative. The derivative of sine x is cosine x. And that means f prime of 0 is cosine of 0, which is, what do you say? 1. Yeah, cosine of 0 is 1. Okay. So the next constant is going to be 1. And we just got to continue like this. Hopefully we can figure out some kind of pattern eventually. F double prime of x would be the derivative of cosine. That's negative sine x. When I plug in 0, f double prime of 0 is negative sine 0, but sine of 0 is 0, so this one's also going to be a 0. So that term in the power series has a 0 coefficient. All right, next one. The third derivative. So the derivative of negative sine x, the sine becomes a cosine and the negative stays like it is. So the derivative of negative sine x is negative cosine x. And then f triple prime of 0 is negative cosine of 0. Cosine of 0 is 1, so this is minus 1. All right? How many of these do you want to do? Let's keep doing this. Yeah. Yeah, actually, if you do one more, you will see that this pattern that we've done so far kind of cycles. If you do another derivative, so this is the fourth derivative. What's the derivative of minus cosine x? It is positive sine x. So we're sort of back to where we started at this point. So the fourth derivative, when I plug in 0, I get sine of 0, which is 0. But you'll see, like, here to here, these are the same, right? And so this pattern will continue. It goes 0, 1, 0, negative 1, then 0, then 1, then 0, then negative 1, etc. All right? So we don't have to keep on doing this forever. That's the pattern. It's not easy to write a formula for that. It's just 0, then 1, then 0, then minus 1. All right? Anyway, so my Taylor series then, I think we can write it out. So remember the formula for the Taylor series? I'll just write it again here. This is what I wrote at the very beginning today. F of 0 plus f prime of 0 times x plus f double, sorry, this one has a 1 over 2 factorial, which is just 2, but I'm writing the factorial so that you remember what it means. 1 over 3 factorial f triple prime of 0, x to the 3, etc., right? This is the formula for the Taylor series. In our case, the constants go 0, 1, 0, minus 1, etc., right? And so our series is going to look like sine x is, so we begin with 0 as a constant. Then the first thing that's not a 0 will be just x, right? Then the x squared term is going to be a 0, so I leave that out. The next one is the x cubed term, which has a coefficient of minus 1. So it says x minus 1 over 3 factorial x cubed. All right, continuing the pattern, the next one would be a 0. So there is no x to the 4 in this series. But the next one is a 1 again. So the next one, which I see, will be plus 1 over 5 factorial x to the 5. After this plus will be another 0 term, so there is no x to the 6. The next one will be negative, so it'll be a minus 1 over 7 factorial x to the 7, all right? And then the next one will be plus 1 over 9 factorial x to the 9, minus, etc. So what you have here is alternating signs using only the odd terms, right? The odd degree terms. This is the series for sine of x. You should put that in your big list of important serieses, which I encouraged you to start a list of those last time. This is the series for sine of x. All right. You could, if you want to, write this like as a summation from n equals 0 to infinity. What we have here are only odd powers. So when I write this as a sum, I'm going to write something like x to the 2n plus 1. This will give me odd powers of x. Starting when n is 0, I get x to the 1. When n is 1, I get x to the 3, and so on. This is odd powers of x. And then the coefficients have alternating signs. So the way you make that happen is with this, minus 1 to the n. And then they also have that factorial thing. So it's a 1 over... Should have left myself some more room in here. Can I? It's the factorial, but it's not n factorial. It's this number, 2n plus 1 factorial, right? The odd numbers. This is a formula for that series written as a summation. In my opinion, this... Huh? Give it a moment. That summation is a little more confusing. In my opinion, the thing in the box is for most purposes more useful. The one in the box.
From here, what's our interval convergence?
Yeah, that's what I'm going to talk about just next. And actually, that's why I wrote the summation formula here, because if you want to find the radius of convergence, the interval of convergence, I don't know what's going on. Put that in the class evaluations. The blue screen comes up, and he doesn't know why. It's true. I have no defense for that. What was I saying? The reason actually I wrote this summation is because I intend to do the ratio test to find the radius of convergence, and to do the ratio test, you got to do that an plus 1 over an thing, and then it's more useful to write it in this way. I'm going to quit my other apps here. Sorry. It's the computer, man. I blame it on the computer. Okay. So this is the series for sine of x. How about the convergence? Let's see if we can work that out. The convergence is, I'm going to use the ratio test like we always do. And I'm going to do the old L equals, right? Lim n goes to infinity. And then you got to do absolute value, an plus 1 divided by an. Where those a's are the terms that you see inside the series. The whole thing, including the x, all right? That's what the a's are. So this one, to get a n plus 1, you got to go in that formula that I circled and replace the n with the n plus 1. It looks like, okay, absolute values. All right, I'm replacing n with n plus 1. I get minus 1 to the n plus 1. 1 over, this gets a little nasty, but it's 2 n plus 1 plus 1 factorial, right? I replaced the n with a n plus 1. And then x to the power 2 n plus 1 plus 1, all right? Everywhere I see n, I replace with n plus 1. And then this is all divided by the other thing, which is just an, which is just that stuff circled, written exactly as is. So it's minus 1 to the n, 1 over 2n plus 1 factorial, x to the 2n plus 1. All right. Sorry about my messy looking absolute value signs. Okay, let's rearrange this, gather together, and hopefully cancel a lot of stuff. First of all, when I do the absolute value signs, as usual, they don't change very much, although in this case they are going to wipe out the minus 1 to the power whatever. Those things just become irrelevant when you take the absolute values. Other than that, they just squeeze in completely around the x's. So as far as the x's goes, I'm going to end up with absolute value x to the, can we simplify inside that exponent? What does this equal when you, yeah, it's n plus 1 in there. Sorry, it's hard to read. Yeah, 2n plus 3 is what you're going to get from that. You distribute the 2 first, it makes 2n plus 2, and then plus 1, so it's 2n plus 3. Okay, so this is going to be x to the power 2n plus 3 divided by absolute value x to the power 2n plus 1, right? I just gathered together the x's. And then the other part, which is left over, is the factorials part. And I'm going to sort of flip everything over because everything is in denominators. So the factorial parts, I will have a 2n plus 3 factorial on the bottom and a 2n plus 1 factorial on the top. All right? Once you rearrange all the fractions appropriately, this is what you end up with. Okay, let's continue to cancel if we can. How about the x's? I think this is a little easier. I have x to the power 2n plus 3 over x to the power 2n minus 1, plus 1. You should subtract the exponents. I think all you get left over is x squared on the top, right? If you subtract those exponents, you end up with x to the 2, or I mean absolute value, of course, x to the 2 in the numerator. And then the other, the factorial thing, when you have a fraction of factorials, typically what happens is they all cancel except you have something left over either on the top or on the bottom. Can anyone say what's it going to be on this time, in this one? On the top we have all numbers up to 2n plus 1. And on the bottom we have all the numbers up to 2n plus 3. It is a 1 on the top. All those guys on the top will cancel. You're multiplying every number up to 2n plus 1. Those also occur on the bottom. Yeah, what's left over on the bottom would be 2n plus 3, and actually also 2n plus 2, right? Because what you have on the top is, little sidebar here, on the top it says 1 times 2 times 3 times everything up to 2n plus 1, right? And on the bottom it says 1 times 2 times 3 times everything up to 2n plus 3. That means, whoa, that means in particular you do get 2n plus 1, but you also get 2n plus 2, and then finally you get 2n plus 3. Sorry I'm writing so small. Anyway, all of these cancel. What remains is 2n plus 2 times 2n plus 3 on the bottom. All right? Anyway, what do you get when you take this limit? The absolute value of x squared just kind of hangs out, and that fraction in the front gives you a 0 because we have n's in the denominator, which are going to become infinite. when I go n goes to infinity. So this becomes 0 times absolute value x squared, which is 0. All right? So that means the L equals 0. So L is less than 1 for any x. And that means the series converges for every x. So the series converges for every x. So the radius of convergence is infinity is the way we write that. Yeah.
So would we say that's technically absolutely converging, but like in a different way than the other series, since it is convergent for all values in x? Or would that just
Absolutely convergent means something else. Although this series is absolutely convergent, it's not because of... Oh, no, you're right. Yeah, when the L is less than 1, the series is absolutely convergent, which means if you took the absolute values of everything, then it would still converge. Yeah.
okay.
Although that's not really... I mean, we're not going to take the absolute values of everything, because then if you did take the absolute values of everything here, it wouldn't equal the sign anymore. So that would not be really a useful thing to do. But yeah, what you said is correct. It is absolutely convergent. We just don't care in this context. Yeah. So the radius of convergence is infinite. Another way of saying that is the interval of convergence is just everything, right? On which interval of x values does it converge? Well, we just said it converges for every x value, and so to write that as an interval, it would have to be just the interval minus infinity to infinity. All right? So the series for sine of x, when you put this in your big list of series, you should also write down at the same time the r, the radius is infinite. All right? Any thoughts about that? You can actually see some interesting properties of the sine function just by looking at the series. Like a lot of, when you learned trigonometry, you proved a lot of things about the sine. A lot of those things actually you can deduce just by looking at the series. For example, just by looking at the series, you can tell, I don't want to scroll away from this, although what I'm about to say is a minor point. Well, I'll scroll away from it. You can look at that at the same time, right? Just from the series, we can see, for example, what is the sine of 0? Now, I know because I know trigonometry, the sine of 0 is 0, but looking at the series, you can also tell that the sine of 0 is 0, because if you plug x equals 0 into the series, you get, 0 minus 1 over 3 factorial, 0 cubed plus, right? Times 0 to the 5th. It's 0. And in similar ways, a lot of the classic properties of the sine function you can deduce from the series rather than from drawing little triangles, right? Which is kind of cute, I guess. All right. Anyway, I would like for you all to try all that same stuff, but with the cosine. So try the same for cosine x. So this might take a little, I mean, it just took me 20 minutes to do that, although it should go a little faster because it's very similar to what I just did. So I would like to find the series and its radius of convergence. All right. We'll take some time to do that. I hope the folks at home are doing all right.
Just checking my basic math skills. Do you have the derivative of cosine sine?
The derivative of cosine is negative sine. Yep.
Basic math skills are not good.
Yeah, if you mess it up at the beginning, you're screwed for the whole thing. So you might as well get it right to start off with. bandwidth. We are trying to write the series for cosine in the same way. Any questions from the folks on the Zoom? How come you don't come to class no more? That's my question. It's up to you, of course.
For the derivative of f, it's only the full factorial, right?
Yep. I gave you a hint. It starts with a 1.
Struggling to find the actual series. Like I found these but I'm struggling to find this series.
Good.
The difference between the difference between the yeah.
Any questions from the folks in the Zoom? take another couple minutes and then we'll discuss it. Any questions in the Zoom here? I'm good for it.
Also, 2n over 2n plus 1 simplifies to 1 over 2n plus 1 times 2n, right?
The 2n would also cancel in that case.
So it would just be 1.
But I don't.
Just 1 over 2n.
Yeah, but I don't think that's what you get. I think the fraction should look a little different from that. Let's talk about this. So as I'm walking around the room, everybody got this far. At least I hope that you folks at home got this far too. The cosine has only the even powers of x. It alternates the signs just like the sine. So the difference in terms of the power series, the difference between sine and cosine is just odds versus even powers of x. All right? I'm sure you learned at one point in your life that sine of x is an even function. Sorry, sine of x is an odd function and cosine of x is an even function. That fact is also evident by looking at the power series. Anyway, let's do the radius of convergence thing. So the L would be something like lim n goes to infinity. I do an plus 1. So that's minus 1 to the n plus 1. 1 over, here's a, make sure you do this right, 2n plus 1 factorial. 2 times n plus 1, the whole thing factorial. That's going to distribute and become 2n plus 2. Anyway, x to the power 2, n plus 1. Okay, and then dividing by an is just that same stuff written exactly as is. 1 over 2n factorial, x to the power 2n. All right? You got to distribute those 2's, which will change things around a little bit. Anyway, when I do the absolute values, it kills the minus 1 to the power whatever. And then sort of hugs around the x's. After rearranging everything, it's going to look like, for the factorial parts, I will have 2n factorial divided by 2n plus 2 factorial, distributing the 2 there. And then for the x parts, I have absolute value x to the 2n plus 2 over absolute value x to the 2n. Right? You cancel the x's, you get x squared remaining in the numerator. Absolute value, of course, of x squared. And then the when I cancel the factorials, what do you get here? On top, I have all the numbers up to 2n. On the bottom, I have all the numbers up to 2n plus 2. Right, the bottom has 2 extra numbers, right? All those numbers, they go up to 2n, but then they also have 2n plus 1 and also 2n plus 2. So this is 1 on top and then 2n plus 1, 2n plus 2 on the bottom. All right, great. I take the limit. That fraction becomes 0. This gives me just 0 times absolute value x squared, which is just 0. So the L is 0, just like happened for the sine. So L is 0, so it converges for every x, right? Radius of convergence is infinite. So when you put this in your little chart of serieses, it's the radius is infinity. All right, convergence is for all real numbers x. Excellent. Anybody got any questions about that? I hope that everybody, hope it worked out for everyone. I feel good about it. All right. By the way, can we just I don't want to go through this whole example in detail, but actually, I'm not going to say. I want to fit in our remaining 15 minutes what I was going to say next. I'm about to describe to you one of my favorite things in all of mathematics. Are you ready for this? I remember when I was a young lad and I first learned this fact, my mind was completely blown. And I knew in that moment that I wanted to be a mathematician. That's not actually true, but I was very impressed. There was no single moment when I knew that I wanted to be a mathematician. Here's a crazy fact, all right? Check it out. When you look at the series in your list of series, you have e to the x, which looks like this. All right? And actually, I'm going to write a few more just for the sake of what I'm about to say. I want to see a few more terms here. X to the 4, 1 over 5 factorial, x to the 5. If I write sine and cosine, what do you look like? So sine gives me only the odd terms, 1, and I'm going to try and sort of, sorry, not 1. 1 is an even term. I'm going to try and line them up. The series for sine is this, right? And the series for cosine is 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4 and more stuff, all right? It looks to me like if you were to sort of add up the sine x and the cosine x, they have these gaps, but they would sort of fill each other in, and they kind of add up to be e to the x, although it doesn't exactly work out because of the signs, right? The negative signs, the minuses and the pluses, they don't quite add up in the way that you would like. So can I just say sine x plus cosine x almost looks like that is a good idea, although it doesn't work that way, because this, if you had numbers like this, that's not the same as this. You can't, there's like an inequality there, the triangle inequality, but it's not equal. And so it's not true that, yeah, absolute value sine x plus absolute value cosine x, they don't add up to e to the x. I imagine people, when they saw this, were kind of surprised. I mean, it is a surprising fact that you can even write sine and cosine in this cute way as polynomials. But the fact that those two polynomials, if you were to combine them somehow, they almost look the same as e to the x is really interesting. Somebody actually figured out how to do this properly, and this is usually attributed to Euler, the mathematician Euler, which some people say Euler, but those people are wrong. This is a German name. It should be pronounced Euler. Euler realized, or maybe somebody else, it's not clear if Euler was the very first person to have this idea. But here's Euler's crazy idea. If you use x, instead of x, use I times x, where I is this imaginary number, the square root of minus 1. Perhaps you've heard of imaginary numbers. They're a real thing. They're not fake. They're just not, they don't qualify as real numbers, but there is a way to work with things like the square root of minus 1. It's not a real number, but it is a thing that you can still work with. Check it out. What if I, my intention is to plug in, instead of x, plug in ix to these serieses. All right. What it looks like is yeah. So I is what it is. I is the square root of minus 1, right? What about I squared? I don't know if you guys are into i's. Can you tell me what is I squared? It is -1, right? If I is the square root of -1, that means that I squared is -1. Okay, what about I cubed? I'm trying to just write the powers of I. Well, this would be I squared times I again. That's what I cubed would mean. So I squared is -1. So this is actually negative I, right? I to the 4. Well, this would be I squared times I squared, but that's -1 times -1, which would be +1. All right. What about I to the 5? Actually, I to the 5 would be I to the 4 times I, but this is 1 times I. So this is I again. So actually, you have a similar kind of repeating pattern here. You have I, and then I squared is -1. I cubed is -I. I to the 4 is 1, and then I to the 5 will be I again. And this sort of pattern will continue. You get I, and then -1, -I, 1, and then I again, etc. These are the powers of I. This is how I works when you take powers of I. Sorry, I'm off the bottom there. All right. Anyway, here's Euler's big idea, or somebody's big idea. What if I use Ix in this series for e? E to the power Ix. What are you going to get? Well, I'll write the series for e to the x again. It's 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed. I'll just go up to the 4th term. What if I use Ix instead of x? E to the power Ix. It's 1 plus Ix plus 1 over 2 factorial Ix squared, 1 over 3 factorial Ix cubed, 1 over 4 factorial Ix to the 4, etc. Now, we can simplify this by doing those powers of I. Split out the powers of I in there. This says 1 plus Ix plus 1 over 2 factorial. This will be I squared times x, but I squared is -1. So actually, I'm going to write it this way. Minus, right? I squared is -1. So you get -1 over 2 factorial x squared. Plus, okay, I cubed. Actually, it's not going to be plus. Because I cubed, I said before, I cubed is minus I. So this will say minus I times 1 over 3 factorial x cubed. The next one will be I to the 4, which is 1. So this is just plus 1 over 4 factorial x to the 4. Right? And now, actually, what we are looking at is, I do have the signs alternating in the way like a sine and cosine would be. And if you split apart the odd ones, the odd terms, they look like Ix minus I 1 over 3 factorial x cubed plus the next one would say I 1 over 5 factorial x to the 5, right? And the even terms would be 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4. All right, this is actually just equal to cosine x. That is the series for cosine. What's the other one? Does the other one look like anything? It looks like sine, although it has a bunch of i's on it. Actually, it just has an I like distributed on everything. So the first one is actually I times sine x. And it is a true fact. If you add these together, you get this, right? And so this is Euler's discovery, is that e to the ix is equal to cosine x plus I times sine x. This is a relationship between sine and cosine and the function e to the x. All right. This is kind of shocking just because, I mentioned this last time. You know, people like to think about, is mathematics discovered or invented? Mathematicians feel like we are inventing things as we create these concepts. But oftentimes the concepts we create behave in ways that we did not intend for them to behave. What you see here are sine and cosine, which were invented like by the Greeks, you know, to do geometry. And it turns out you can combine them in a way and get the function e to the x, which was invented like by European capitalists trying to study compound interest, right? These were invented to do completely different things, but it turns out they fit together in this way. This is referred to as Euler's formula, and there's a simpler version of this. What if I plug in x equals pi? The left side says e to the power I times pi, and the right side says cosine of pi plus I times sine of pi. And the sine of pi is 0, right? Sine looks like this, where that's pi. And the cosine of pi is -1. So this actually is -1 and then plus I times 0, which is 0. So the whole thing says e to the I times pi equals -1. And this is sometimes written, if you just add the 1 to the other side, e to the I pi plus 1 equals 0. This is called Eulers Identity. Eulers Identity. A lot of this is like if you want to be edgy, you get this tattooed on your arm or something. A lot of people have tattoos of Eulers Identity, and this is widely regarded as the greatest formula, single formula in all of mathematics, and one of the classic examples of what people think of when they think of mathematical beauty. If you ask me like why I'm interested in mathematics, actually, I'm in it for the mathematical beauty. It's this, and what that means is not like pretty pictures. What's beautiful about this formula? This formula includes all the like most important numbers in all of mathematics. If you were like stuck on an island and you could only bring 5 numbers with you, on your list of top 10 numbers of all time, most useful numbers, 1 and 0 absolutely should be at the top of your list. Plus pi. If you want to do calculus, you better throw in e. And if you want to do algebra, you should use I. These are the most important constants in all of mathematics. Each one was created by wildly different people to do different things, right? Like 1 is the basic unit of all counting, and so any human being would come up with the number 1. The number 0 is also a simple idea, but it took a long time for human beings to come up with the number 0, and it was basically like the Indians and the Arabs. Pi, of course, was the Greeks. E was European capitalists, and I was also a product of sort of modern European mathematics. But I is intended to do algebra. Anyway, these 5 numbers are the basic building blocks of completely different areas of mathematics, and there is no good reason why they should all be related in such a simple way. But they just are. You can, and if you don't believe me, you can even do this on your calculator. If your calculator can handle imaginary numbers, you'll get -1. It really is equal to -1. This kind of thing is, I'm not sure actually if Euler thought of all of this in terms of series, although I suspect that he may have. This kind of thing becomes, they're really, before you look at the series for e to the x, there's no reason for anyone to think that this would be true. But it comes from looking at these 3 series and realizing that somehow you should be able to add together the sine and cosine and make it add up to the e. What the missing ingredient is the I. You need the I to make that work out. All right. Euler's identity. If someone asks me, I'm thinking of getting a math tattoo, what should it be? This would be mine. This is the go-to math tattoo. All right. All right. I guess that's time. We will discuss more next time about the series, and we'll have our final quiz. See you all then. That's right. Yep. Yes, homework's due today. See you later.
Thank you.
Bye-bye.